In this video, we are continuing with the topic from the last video where we had defined the normal, multivariate normal with parameters mu and capital sigma like this. We started with x1 to xn IID normal 0, 1. Then someone gave us mu and capital sigma. Then we constructed a random variable as ax plus mu, where A is any matrix, any m by m matrix with sigma equal to AA transpose, and declared the distribution of this to be the multivariate normal. Now the natural question was this word any, because there may be infinitely many capital A's for which this equation will hold. So we need some way of justifying that whatever A you choose, the distribution of the resulting y should be free of the particular choice of A. It should depend only on mu and capital sigma, and that is what we are going to prove in this video. Now, in order to show that two distributions are the same for two different choices of A, we can either work with density or CDF or something, but the trouble is, as we have seen, even when m equal to 1, that singular normals are also part of this, where you have got just degenerate cases that do not have density. So we cannot talk with density and do the proof in general. We can of course work with CDF, but CDF is extremely complicated, so we cannot use CDF either. So what we shall do is, we shall use characteristic function. Now in case of univariate things, we had just this definition, but now our y is actually a vector, so we need to first generalize that. When we have a single random variable, then we had characteristic function defined like this, but now we have a random vector. So now this characteristic function of xi, of the random vector xi, of random vector y, will require not just a single t, but a vector of t's. So t1 to tm, and this is also the vector y. Now this will change to expected value of e to the power I times t1y1 plus dot 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 tmym. So this entire thing, we can denote it as a t vector. So that t vector will be in Rm. So that is the definition of characteristic function of a random vector. Now just as in the univariate case, characteristic functions have the two very useful properties. One, characteristic function always exists for any Rm valued random vector. In case of m equal to 1, we have already seen that it always exists for any real valued random variable. Here it is Rm valued random vector. And secondly, the property that gives characteristic function its name, it uniquely determines the distribution. By this I mean, if we have two random vectors y and z such that their characteristic functions match, then we can always say that y and z must have the same distribution, irrespective of whether they are discrete, continuous, has density, whatever. It is a perfectly general fact. Now we are going to use this to our multivariate normal setup. Here is a quick reminder of the setup. We have x vector x1 to xm, where xi is our IID normal 0, 1. Now we are given some vector mu and an NND matrix sigma, which we have written as A into A transpose. Then we are writing y equal to ax plus mu. Our job is to show that the distribution of y depends on mu and sigma and not the particular A that we have chosen to decompose sigma. Now we have to work with distribution of y. We have already noticed that this distribution may or may not have density. Its CDF is complicated. So we are going to actually show that the characteristic function of y depends on mu and sigma and not on a. In order to arrive at the characteristic function of y, we shall start with the characteristic function of x. This characteristic function is expectation of e to the power I, t1 x1, etc. up to tm xm. Now, because all the xi's are independent, so it nicely factors out as product from j running from 1 to m, expectation of e to the power I tj xj. But this we quickly recognize as the characteristic function of xj evaluated at tj. Xj's being normal 0, 1, we already know that their characteristic functions are of the form e to the power minus t square by 2. So we are going to apply this for tj in place of t. E to the power minus half summation tj square, because each one of them contributes a tj square. When you are multiplying the exponentials, the exponent becomes the sum. Now this we can write using vector notation as e to the power minus t transpose t, that is dot product between t and itself, or the norm square of t, divided by 2. So now we want to find out the characteristic function of y, which is by definition expectation of e to the power I t transpose y. Just understand that this is nothing but t1 y1 plus t2 y2 plus t3 y3 up to tm ym. So we are writing the entire sum just like this in terms of a matrix multiplication. But we know that y is given by this, hence this is expectation of e to the power I t prime ax plus mu. I have just replaced y by its definition. Now this mu part has nothing random, so it will come out of the expectation as e to the power I t prime mu, that's a constant, comes out of expectation, times expectation e to the power I t prime ax. Now this is very much like the characteristic function of x, except that the role of t prime is played by this t prime a, which we write as a prime t whole prime. So once you take transpose, this will become t prime and a transpose transpose will become a. So it is just the characteristic function evaluated at a transpose t. We already know that the characteristic function is this, so I will just plug it there. E to the power minus a transpose t transpose, just t transpose, and then without the transpose, so t transpose t by 2. Now let me just manipulate this a little bit. Once I take the transpose inside, I shall get t transpose a, so this is a transpose transpose, and this a transpose t is as before. So you see, I am getting a transpose, which you remember is nothing but sigma. So this thing just becomes t prime sigma t. So we see that this thing is not depending on a explicitly. It depends on mu, it depends on capital sigma, but as long as you take any a which satisfies this condition, it is not going to depend on the particular choice of a. That's exactly what we wanted to show. And as a byproduct, we have also learned that the characteristic function of normal mu sigma is e to the power minus t prime sigma t by 2 plus I t prime mu. With this theorem still fresh in your mind, try to work out this. I tell you that y has a bivariate normal distribution with some mu and sigma. I give you the characteristic function, which is given like this. Now your job, so by this I mean e to the power this, so e is a little here. Your job is to find mu and sigma based on this information.